All right, welcome to the Explainer. Today, we're going to demystify machine learning. And I mean, really break it down. We're going to start with something as simple as a line on a graph and build all the way up to the kind of complex AI that's literally changing our world as we speak.
So it all boils down to this one single question, right? How can a machine actually learn from experience? I mean, think about it. It sounds like science fiction, but the answer to this is already reshaping everything around us, from your daily weather forecast to the hunt for brand new medicines. For the longest time, programming was like giving a computer a super detailed recipe. Step one, do this. Step two, do that. No exceptions. But machine learning, it flips the script entirely. We don't give it the recipe. Instead, we just show it the finished dish, tons and tons of data, and say, okay, you figure out the recipe. It has to find the patterns all by itself. Now, the most common way we do this is with something called supervised learning. And honestly, the best way to think about it is like you're studying with flashcards. We show the machine an example, let's say a picture of a cat, and we give it the answer, cat. We just do that over and over and over again, thousands, maybe millions of times, until it finally gets it and can spot a cat all on its own.
Okay, so let's see what this looks like in the real world. We're going to start with the absolute basics. I'm talking about the simplest task you can imagine, just trying to draw a straight line.
So picture a bunch of data points just scattered on a graph, right? The job of a really basic model, something called linear regression, is to look at all those dots and find the one single straight line that best cuts through them, the one that really captures the trend and gets as close as it can to all those points.
Okay, but how? How does a machine actually find that one perfect line? It's not just throwing darts in the dark, believe me. There's a really clever process going on behind the scenes. It's this really cool process of, smart trial and error called gradient descent. So here's how it works. First, the machine just draws a totally random line. Then it measures how wrong it is. That's what we call the loss or the error. The next step is the magic part. It figures out which direction to nudge the line to make it a little less wrong. It makes a tiny adjustment, and then it just repeats over and over again until that error is as low as it can possibly go.
There's a fantastic way to picture this, and it comes from some developers at Google. Think of all the possible lines as a landscape with hills and valleys. The height of the hill is how much error a line has. So our model is like a ball we just drop onto this landscape. What's it going to do? It's going to roll downhill, right? It'll always follow the steepest path down until it settles at the very, very bottom of the valley. And that point, that's our best fit line, the point of lowest possible error. And what's really cool is that for simple models like this, that landscape isn't a complex mountain range. It's more like a single perfect bowl. There's only one bottom. So our ball is guaranteed to find the absolute best answer. It's not going to get stuck in some little dip halfway down the hill. It finds the global minimum every single time. It's a really powerful guarantee to have. All right, but let's be real. The world is rarely a straight line. Most problems are way more complex, which means we need some more powerful tools in our toolkit. So sometimes what you're trying to predict is a number on a sliding scale, like the price of a house or what the temperature will be tomorrow. Whenever you're predicting a specific value, we call that a regression problem.
And then there's the other type of problem. This is when you're not predicting a number, but you're trying to sort something into a category, into a specific box. Is this email spam or is it not? Is this a picture of a cat or a dog? That's what we call classification. And this is where choosing the right kind of model makes a huge difference. Take a look at this. This is from a study trying to predict how well students would do in their courses. These more advanced models, like SVR and XGBoost, were able to explain up to 95% of the variation in student performance. I mean, what that really means is they were incredibly good at pinpointing the factors that lead to success. That's some serious predictive power.
Okay, so we've got models that can find trends and models that can classify things into buckets. But what happens when the data isn't just a collection of points, but a whole network? Where the connections between the points are the most important part. Well, that's where things get really interesting. Welcome to the next frontier.
This is the domain of what we call graph neural networks, or GNNs for short. These are AI models designed specifically to understand data that looks like a web, a graph of nodes, which are the objects, and edges, which are the relationships between them. Think about it. Your social media friends list, that's a graph.
A map of every financial transaction in a bank, that's a graph. Even a molecule is just a graph of atoms and their bonds. The way they work is actually pretty intuitive. It's a process called message passing. Just imagine every single point in the network, every node, basically talks to its immediate neighbors. It shares what it knows. Then, in the next round, those neighbors share that information with their neighbors. After a few rounds of this, it's like a wave of information has washed over the entire network, and every single node now has a much richer understanding of not just itself, but its place in the whole system.
And the real-world applications for this are just mind-blowing. We're talking about discovering new drugs because the GNN understands the complex web of relationships between atoms. They're used to catch sophisticated fraud rings by spotting weird patterns of connections that a human would never see. And yeah, that recommendation you just got on Amazon, that's probably powered by a GNN that understands the massive network of what people buy together.
But all of this incredible power, this complexity, it comes with a price. A really big one, actually. And it's a challenge that the entire field is trying to solve right now.
So here's the deal. The more powerful and complex these models get, the harder they are to understand. It's like we can see the answer it gives us, but we have no idea how it arrived at that answer. The inner workings are just a complete mystery. And this is what everyone in the field calls the black box problem.
So, to try and build trust in these systems, researchers are trying to crack open that black box. And they're basically tackling it from two different directions. The first is what we call local interpretability. That's asking, okay, why did you make this one specific decision? The other angle is global interpretability, which is a much broader question. How do you make decisions in general? What's your overall logic?
And all of this leaves us with a really, really important question for the future of AI. As these machines get more and more powerful and start making decisions that affect our health, our money, our safety, how do we make sure that we can actually trust what they're telling us? Figuring that out isn't just some tech problem. It's absolutely critical for all of us. And that's our explainer for today.